I'm Eric Scheidley, and this is Astronomy Fundamentalized, Lecture 13, Stellar Evolution. In this lecture, I'll describe the life cycle of low-mass stars, and in doing so, reveal the fate of our very own Sun. It may have occurred to you, in looking up the night sky and seeing all the stars, what is it that makes the stars shine? Where does the light come from? Often we refer to the stars as burning in the heavens above. So we imagine for a second that it's chemical burning, that the stars are literally on fire. Well, if that were the case, we'd have to imagine what sort of fuel is it that makes up stars. And in fact, any type of fuel that you can possibly imagine, even with stars being as massive as they are, chemical burning would cause stars to burn out in only a few thousand years. And so it couldn't possibly be the reason for stars shining the way they do. Perhaps what's going on really is that the stars begin their life being extremely hot, all the stars in the universe, very, very hot, and that they're cooling down, and that we're just looking at them at a time when they haven't cooled to the point where they stop giving off light. Well, this would, again, give us only a few thousand years. And not only that, over the course of a star's lifetime, like our own sun, for example, about 4.5 billion years old, it would have cooled significantly such that the amount of radiation given off would change significantly on short time scales, which would be very bad news for us. Another possibility that you may not have considered is that it could be gravitational contraction. If I take my pen, I happen to be holding here a pen, and hold it up above my desk, and release it, it falls to the surface of the desk. It's gravitational potential energy being converted into kinetic energy of motion. And in fact, ultimately my pen hits the table and stops moving. Where is the energy gone? Well, heat has been generated in this process. It's difficult to tell and almost impossible to measure, but when I drop my pen from a certain height and it hits the desktop, a little bit of heat is generated. Of course, stars are fantastically massive, so perhaps what's going on is that as the star compresses, the gravitational potential energy is converted into heat. Well, once again, this is completely insufficient to account for the billions of years of burning, and in fact, the radiative intensity, if it was gravitational contraction, would not be sufficient to explain the brightness of even our own sun. For a very long time in the history of astronomy, this was a complete mystery, where stars got their energy from. It was because we lacked a fundamental understanding of the behavior of matter and energy in our universe. This lack of understanding was rectified by Albert Einstein when he developed what is now known as the mass-energy relationship, or the mass-energy relation, arguably one of the most easily recognizable equations in the history of all of science. E equals mc squared. We need to know what the symbols stand for. On the left-hand side of the equation, the capital E stands for energy. Energy in all of its forms, whether it be gravitational potential energy, kinetic energy, the thermal energy associated with the random motions of molecules and atoms. Every form of energy that you can imagine, there on the left-hand side, energy, including the energy of light. On the right-hand side of the equation appears an M. That M stands for mass. The very common everyday usage of the term mass, the mass of a paperclip, the mass of the Earth, the mass of the Sun, the mass of the universe, a certain number of kilograms. The C is the speed of light. Not only is the speed of light a very large number, 3 times 10 to the 8th meters per second, but when you square it, C squared would be 9 times 10 to the 16th meters squared per second squared. An extraordinarily large number. The conclusion that we draw from this, all of the sudden, and quite startlingly, is that if I have a very small quantity of mass, that mass contains within it an amount of energy which is fantastically large, because c squared is a particularly large number. It was immediately realized after this equation was derived by Albert Einstein, if one could harness this energy, it would have a great deal of destructive power. Unfortunately, that's the first conclusion that we drew. And we were able to construct from this notion nuclear weapons. When a nuclear weapon is detonated, matter is literally converted into energy. If you take a course in chemistry, you may be told about an idea of conservation of mass, that whenever a chemical reaction takes place, the number of atoms you start off with has to be equal to the number of atoms that you finish off with. And the truth is that that's only legitimate statement in the case of chemistry, where the energies don't get very, very high. But in very extreme cases, at very, very high temperatures, the amount of mass in any event is not necessarily conserved. Mass can cease to exist, and in its place, a quantity of energy given by this relation. That means that if an object like a star has a fantastic amount of mass, it's possible that that mass could, over a long period of time, in the case of our sun, 4.5 billion years, be converted into energy. The process basically shakes down like this. In the core of a star like our sun is a great deal of hydrogen. In fact, a star itself is mostly hydrogen. The hydrogen is left over from the creation of the universe when the first protons were formed. A hydrogen atom, in fact, is one proton and one electron in association with each other. Well, here, in a star, at the core of a star, I get temperatures in the order of millions and millions of degrees. These protons are moving around so rapidly that their natural repulsive force is insufficient to prevent them from getting very, very close to each other and fusing. The process is known as nuclear fusion, when subatomic particles come together and create new products. Now, the situation shown here in the diagram is extremely simplified because there are intermediate steps that take place. Leaving out all of the details, ultimately what happens is 4 hydrogen atoms. Here, only the protons are shown because the temperature is so large that the electrons have dissociated from the protons and they're out floating off somewhere doing their own thing. So these 4 protons come together and form a nucleus that has 2 protons and 2 neutrons. If you remember your chemistry well enough, you recognize this as helium. So 4 hydrogen atoms fuse to form 1 helium atom. Now there are some other products as well. Notice that there are 2 gamma rays that come out of here. Gamma rays are just very, very high energy light. They have a high frequency, they have a short wavelength, and therefore they have a high energy. In between the 2 gamma rays associated with the black arrows are 2 neutrinos. Solar neutrinos are very interesting to physicists because they give us some insight into these nuclear reactions that are taking place. And although we have the general idea, to this day they're not explicitly, perfectly well understood. And so studying those neutrinos is very interesting to us here on Earth. And as it turns out, the neutrinos are very non-interacting particles. They travel through the star, interacting very little with matter and out into space, and ultimately come to Earth, where with an extreme amount of cleverness, it's possible for us to detect those neutrinos and observe their properties. From the 2 pink arrows here, I have 2 particles labeled E+. These are actually antimatter electrons, and they're important because these 2 antimatter electrons will invariably encounter very rapidly after the creation of this helium nucleus, very rapidly encounter conventional matter electrons. When that takes place, an E+ and an E-, an antimatter electron known as a positron and an electron come together. They destroy each other again and create 2 gamma rays. So really what I get out of this process is 4 gamma ray photons and a helium nucleus. It's interesting to point out here that when this process takes place, matter has been converted into energy. Because if I calculate the total mass of the 4 protons together, that mass is greater than the mass of the helium atom plus the neutrinos and the electrons associated with it. It's greater than the mass of the products. Where did the mass go? Well, according to E equals mc squared, that mass was converted into the luminous energy of the gamma rays that are created. Here is probably one of the most amazing facts that you will learn in all of astronomy. In the core of our sun, this process proceeds where hydrogen is converted into helium, and the helium is less massive than the hydrogen that was used to create it, and so mass is converted into energy. Our sun converts 2 million tons of mass into luminous energy every second. Pause for a moment and take that in. 2 million tons of matter converted into energy in every second. Immediately your mind might go to think, well, why doesn't the sun just dissolve then and disappear? Bear in mind, the sun is fantastically large, 10 to the 30 kilograms, and so it has plenty of hydrogen fuel to undergo this process. So these gamma ray photons are created, but the core of the sun is opaque. So where do they go? The gamma rays are immediately absorbed by particles and emitted by particles in random directions. They essentially wiggle around inside the core of the sun, randomly going this way and that, being successively absorbed and re-emitted, ping-ponging around amongst all of the particles, contributing to the very high energy of the core of the sun. Ultimately, they wiggle their way out to the chromosphere, where the energy of those photons is converted into visible light. Thankfully, it's not these gamma ray photons themselves that come to Earth, because they would be lethal to all life on Earth. We'd all be dead. So the gamma rays make their way to the surface of the sun. Interestingly enough, that random process of that light making its way to the surface takes on average, about 10,000 years for a gamma ray photon created in the thermonuclear process at the center of the sun to work its way out to the surface. About 10,000 years. Very remarkable. So this is the process by which stars get their energy. And it's also a way that stars maintain their equilibrium. We all know that, or we've heard before, that nuclear processes, particularly fission nuclear processes that we do in our nuclear reactors to produce electrical power, they have a tendency to run away with themselves. As energy is released in the nuclear reaction, it increases the energy of the environment, thus increasing the likelihood of additional fusion. So it's possible that the process could run away, but stars have a very natural mechanism for regulating the rate at which the nuclear process proceeds at the core of the star, and it's extraordinarily important to us here on Earth. The way it works is this. All of the mass of the star exerts a gravitational force on itself, drawing the star together. The gravitational force of the star is compressing itself. This is the reason why the temperature at the core of the star gets large in the first place. The pressure of all of that mass bearing down on the center of the star creates the very high temperature. But then the nuclear process proceeds, and radiation inside the core of the star is working its way outward. Believe it or not, light actually exerts pressure. If I turn on a flashlight and point it at my hand, I cannot feel it. In fact, it's very, very difficult to concoct an experiment where you could, in principle, measure this. But the light from the flashlight is actually pressing on my hand with a force of pressure. In fact, if I were in space, I could use a very powerful laser beam as a method of propulsion, pointing it out this odd way, just as I would point the direction of my rocket nozzle in order to send me going in the opposite direction. An additional unnecessary detail is that in this way light has momentum. Nevertheless, as the radiation forces its way outward to the surface of the star, it exerts an outward pressure. So the way it works like this is in equilibrium. If the pressure becomes too great, the temperature in the center of the star gets higher and the nuclear reaction proceeds at a faster rate. But that means there's more radiation, which means there's more outward pressure, which cancels out the inward pressure of the gravitation. The star begins to expand a little bit. But that reduces the temperature at the core of the star, which reduces the rate at which the reactions take place, which reduces the radiation pressure and causes the star to compress. The compression then causes the star to heat up, which, well, you see how it goes. These two effects, radiation pressure outward and gravitational pressure inward, are acting at cross purposes on the star. And so they form a sort of equilibrium which keeps the temperature at the core of the star very constant and keeps the nuclear process proceeding at a very constant rate. It's extraordinarily important for us on the surface of the Earth because it regulates the solar output so that the amount of energy that we receive on Earth from the star is nice and uniform and consistent. Otherwise, we would have fantastic variability, which would make it difficult for life on Earth to survive. Here's a diagram which gives you a kind of three-dimensional perspective of our stellar neighborhood. Here we have the sun at the center of the diagram, surrounded by all of the stars in our stellar neighborhood. Maybe some of the names of these stars are familiar to you. Alpha Centauri, which is the star that is closest to Earth, which is about 1 parsec away. Barnard's star, you may have heard that name. Epsilon Arandi is a favorite of mine. Sirius, which is a binary star system, Sirius A and B. Procyon. All of these stars are in our basic stellar neighborhood. When we look at these stars, they all have different luminosities. They all have different amounts of brightness. There's a principle involved in here when it comes to stellar luminosity, and it's one that bears a little bit of explanation. Imagine that I have a star of a certain brightness. If I'm standing 1 unit of distance away from that sun, that star will have a certain magnitude. As I get further and further and further away, naturally, that star appears dimmer and dimmer. It doesn't change the fact that the star has a certain intensity. That is, if you were right there at the surface, it has a certain intensity. But if you back off, its apparent intensity, its apparent brightness, its apparent magnitude, the way it looks, decreases in brightness as you go away. And in fact, it turns out that if I go twice as far away, the amount of light that I get in a little square area like that is divided by 4. That is the light that at the radius here in this diagram of D1, the light that came to that square is now distributed over 4 squares. If I go still another unit of distance away, the light that was distributed on 4 squares is distributed to 9 squares, and so it gets dimmer. In this way, we recognize that the light given off by the star diminishes as 1 over the square of the distance. That is, if I have a certain brightness at a particular unit of distance, if I go twice as far away, the brightness of the star will be 1/4. If I go 3 times further away, it'll be 1/9, 4 times 1/16, 5 times 1/25, 6 times 1/36, and so on. This is not a surprising concept because there are other things that work this way. The brightness of a candle certainly works this way. If you get twice as far away, it's quarter bright. If I were giving this lecture live and the sound of my voice were traveling out into the lecture hall, then audience members who were twice as far away from me would hear my voice 1/4 as loud. And this is just because the energy of these physical events is spread out over the surface of a sphere, and the surface area of a sphere is 4 pi r squared. So as the sphere gets larger, the intensity decreases as 1 over the square of the distance. A consequence of this is that I could see 2 stars in the sky, one that is very close and dim, and another that is very far away and bright, and those 2 stars would appear to have the same brightness. This is a critical issue because I would like to know how bright stars actually are. So it's important to appreciate that there's a relationship between the actual brightness of a star, which we call its luminosity, and its apparent magnitude as it appears when viewed from the surface of the Earth. Another interesting aspect of the light that comes to us from distant stars is that it has, well, all the stars that we see in the sky have varying colors. Here in this image, we see a number of stars that are white, as we'd expect as we look with our naked eye. But many of them, the ones that in particular that we get a lot of light from, that is the brightest stars in the image, some of them are red and some of them are blue. And in fact, this is directly associated with the temperature of those stars. Because I know that light that is blue has a very short wavelength, it has a high frequency, it has a very high energy. And light that is red has a very low frequency, a very long wavelength, a very low energy. This is directly associated with temperature. Stars that are blue are stars that are hot, and stars that are red are stars that are cool. So the color that they produce is associated with the surface temperature on that star. For example, an object which is 300 Kelvin, which is a very, very low temperature, by the way. It's like the temperature of a human being. Is not visible at all because the electromagnetic radiation it emits, according to the black body spectrum, is not in the visible range. When the surface temperatures get up on the order of 1,000, 4,000, 7,000 Kelvin, surface temperature of our sun, by the way, being 5,800 Kelvin, the light emitted is in the visible spectrum. But notice, the higher the temperature, the bluer the maximum wavelength, or the wavelength of maximum intensity. Hot stars are blue. Cool stars are red. There's a naming system associated with this, and I just like the look of this particular picture, which is why I included it in the diagram. Unfortunately, it is, for all intents and purposes, backward. I would prefer that it went from left to right and right to left. Nevertheless, I'm going to read off from right to left. O, B, A, F, G, K, M. Is the spectral classification scheme for stars. Point of order, our own sun is a class G2 star. So I would have stars classified as O1, O2, O3, O4, O5 through to O9, and B would have numbers associated as well to account for the spectrum of stars. The point here is that O is the bluest, highest temperature stars, and M are the reddest, lowest temperature stars. You may wonder why the letters seem to be so arbitrary and out of order. It turns out that there was originally a spectral classification scheme that had the stars classified in alphabetical order. That scheme was later abandoned and reorganized, but the classifications remained, and so we have this rather odd order for the thing. There's a mnemonic for remembering this, starting from right to left. It is O, be a fine girl, kiss me. This is the way that astronomers remember the classification. In this diagram, there's a little bit of a concern with the size of these things. It's true that the star classified as O here is blue and therefore very hot, but it need not be the largest of the stars shown. An O-type star could in fact be smaller in radius. Also, we see an M star that is very, very small. That's not necessarily the case. There are M stars which are very, very large. The stars that are shown here are stars in their typical form in their lifetime. These are sort of middle-aged stars. They haven't gone along their evolution yet to the extent that they would change, and so their sizes are appropriate for stars that are in the prime of life. But as stars evolve, we'll find they change their sizes rather dramatically. Any diagram created by astronomers that organizes stars according to their luminous intensity and temperature is referred to as a Hertzsprung-Russell diagram. Go ahead and Google Hertzsprung-Russell diagram and you will get a fantastic number of diagrams with all sorts of stars organized on them, with different luminosities and therefore different apparent magnitudes when viewed from Earth, and different surface temperatures. And you might imagine that you can have stars of any luminosity and any temperature. Why not? What are the rules that govern how luminosity and temperature should be related to each other? Well, it turns out that in fact there are rules. And when I create a Hertzsprung-Russell diagram, like the diagram shown here, stars do not organize themselves just in random locations. Otherwise, I would see a random distribution of stars in this diagram. Instead, what we find is that most stars organize themselves on the diagonal line, slightly curved, drawn from the upper left of the Hertzsprung-Russell diagram to the lower right. This is called the main sequence. But before I get into how the stars are organized with themselves, notice that on the left-hand axis of the diagram is the luminosity. The luminosity on this particular Hertzsprung-Russell diagram is given in such a way that a luminosity of 1 is the luminosity of our sun. Notice, if you look right there on the left where it says 1 on the vertical axis and follow it over to the right, you'll encounter our sun, located on the main sequence. If you go down from our sun, you'll notice that its spectral type is between G and K. Our sun is a G2 classification star, and that's associated with, going from our sun upward, a surface temperature of just less than 6,000 Kelvin. If we continue to the right from the sun to the vertical axis on the right-hand side of the diagram, we see an absolute magnitude of +5, which is appropriate for our sun on the absolute magnitude scale. So this Hertzsprung-Russell diagram is exactly what we asked for. It's an organization of stars according to their luminosity and surface temperature. Notice also we've been given the benefit of color. But this diagram lacks a description of radius. So I just want to say that in general, when you look at these Hertzsprung-Russell diagrams, and you see it drawn this way, that stars that are in the lower left-hand corner of the diagram, stars like Sirius B and Procyon B, are small stars, and stars in the upper right, like Betelgeuse, Antares, Deneb, those are large stars. Many of them with radii hundreds of times larger than our sun, and Sirius and Procyon B with radii a fraction of the radius of our sun. And most of the stars in the main sequence having radii typical of our sun. So here's how the stars organize them. I've already mentioned the main sequence where we see stars like Regulus, Vega, Sirius A, Altair, and Barnard's star, with a variety of surface temperatures and a variety of luminosities. Notice that on the main sequence, in general, the high temperature stars have a higher luminosity, and that low temperature stars have a lower luminosity. This is typical and what we expect from the Stefan Boltzmann law that tells us that the intensity with which stars are going to, with any hot object, is going to be proportional to the fourth power of their temperature. Above the main sequence, we see a collection of stars, in particular Arcturus, Aldebaran, Mira, and Pollux. These stars are what are known as the giants. And we'll come to a moment why giants should exist off the main sequence that way. Above them, stars Betelgeuse, Antares, Deneb, and Rigel are the supergiants. They distinguish themselves from the giants simply because they are much, much larger in radius. As I said, in some cases 100 times greater in size than our own sun. In the lower left-hand corner of the diagram, we have Sirius and Procyon B. These stars are what are known as white dwarfs. Notice that they have high surface temperatures, but generally low luminosities. This is because they are so small that their luminosity is diminished. As compared to the supergiants like Betelgeuse, but that supergiant has a low surface temperature and has a high luminosity only because of its extraordinary size. It takes a little bit of getting used to walking around the Hertzsprung-Russell diagram to understand all of the possibilities for stars, but this format of comparative analysis of luminosity and spectral type of stars is very common to astronomy and worth taking some time to practice and get to know your way around. Here, by the way, is another Hertzsprung-Russell diagram. Notice that the axes have changed slightly. I still have my luminosity axis, but I've lost my spectral classification. And on the x-axis, the lower axis of the thing, I have temperature in Kelvin. going from high to low as I go from left to right. Nevertheless, I have our sun on the main sequence. I have the giants, the supergiants, and the white dwarf regions of the Hertzsprung-Russell diagram specified. When I have a star, like our sun, it begins its life on the main sequence. In fact, here we have, at position 7 on this Hertzsprung-Russell diagram, we have a star with the same luminosity as our sun. We'll just assume that it is, in fact, our sun being typical of low-mass stars in our galaxy and indeed the universe. From here, we're going to track the life of our sun as it proceeds, and ultimately we'll uncover at the end where our sun is going to end up. Right now, our sun is an enormous ball of hydrogen gas, and at its core, the temperature is sufficiently high that hydrogen is being converted into helium, millions of degrees temperature. And that process is going to proceed as long as the hydrogen holds out. But there's only a limit to the amount of hydrogen available at the core of the sun. And when that hydrogen burning at the core begins to burn out, naturally what will happen is the core of our sun will produce less radiation. And as a result, there'll be some gravitational collapse inside of the sun, which will ignite a second stage of hydrogen burning. In a sense, the core of the sun will get larger as an outer level of hydrogen begins to fuse on the outside. As a result of this secondary ignition of hydrogen burning inside of the sun, there'll be a great outward radiation pressure, which will increase the size of the sun, pushing it out into the subgiant branch and ultimately into the red giant branch, where the radius of the sun will increase 100-fold. From position 8 to position 9, its outward radiation pressure causing an expansion in opposition to the gravitational pressure which would reduce it in size. Ultimately, we reach a state where the second hydrogen burning is starting to wear out. There's additional gravitational collapse, but immediately following that gravitational collapse, we have what is called the helium flash, where helium begins to fuse into carbon, and the star begins to develop a core that is carbon ash, surrounded by a helium fusion core, surrounded by a helium fusion shell. And at this point, the gravitational collapse begins to happen, and the radius of the star actually decreases as its surface temperature increases. The surface temperature increases because of the increased nuclear reaction at the center. Once it reaches position 10, it has an opportunity again to gravitationally collapse once again from 10 to 11, where we have what is known as the asymptotic giant branch, where there are multiple shells of hydrogen and helium and a core of carbon and oxygen developing as those many stages of fusion take place in successive shells. Ultimately, what will happen is this fusion will be taking place in the core, and there'll be a bit of gravitational collapse, and the outer layers of the star begin to take on a very low density, and the radiation pressure of the star can begin to push the outer layers off. Ultimately, what's happening is the core of the star is getting smaller while the outer surface gets pushed further and further away. Ultimately, it reaches a point where the outer surface of the star is blown off completely into space, not as an explosion, but as sort of a puff out into space. The result of which is what we call a planetary nebula. It's not called a planetary nebula because it's made of planets, but because it orbits the star as if it were planets in orbit. It's an enormous dust cloud. Shown here, this is NGC 2440. It doesn't, so far as I know, it doesn't have a better name than that, but it's what's known as a planetary nebula. And at the very center, if we look into the pattern of all of the material to the center of the photograph, we can see the burning core remnant of this star that is left behind when it sheds its outer outer shell to produce this planetary nebula. The star that's left behind is known as a white dwarf. So from position 11 at the end of the asymptotic branch, we have a planetary nebula phase where the surface of the star is blown off. Notice that now we have an increase in temperature because naturally the core temperature of the star is much higher than its surface temperature as the planetary nebula is blown away. Also notice that the luminous intensity is quite high. Naturally, this is because the fusion reactions have not yet died out, but they're basically coming to the end of the available fuel. As that happens, we see the luminosity of the star drop off significantly, and naturally its size decrease significantly, because the planetary nebula is no longer part of the star. All that's left is the carbon-oxygen core of the star with some helium fusion going on. The star that remains is very hot, but not very bright, because it's extraordinarily small, less than 1/10 the size of our sun. Such a star is referred to as a white dwarf, and this is ultimately how our sun will end its life. Our sun will not go out in a dramatic supernova explosion, but instead it'll go through a sequence of fusion burning in its core, which will ultimately run its course and peter out as it blows off its surface into a planetary nebula and will diminish to a white dwarf. The white dwarf at stage 13 will ultimately continue to cool, and the surface temperature will decrease, and its color will change, and its luminosity will decrease until ultimately the white dwarf will end as a cinder in space. Such a star is, in our neighborhood, is Sirius B, one of a pair. Here we see Sirius A, bright in the center of the picture, but in the lower left, you see the small dot there, definitely overshadowed by Sirius A, is Sirius B, a white dwarf star, which will get dimmer and dimmer and dimmer until it's, in a sense, a cosmic memory. There's no need to be concerned about this for our sun. Our sun still has billions of years of life left in it before it even leaves the main sequence. So we're not going to have this happening in our lifetime. But ultimately, this is the fate of the star that we call the sun.